Let's talk about exponential decay. It's very similar to exponential growth, except the formula for exponential decay, where something is decreasing over time, is just really changing the sign on one thing in the growth model. And so if we look at the model for decay, we see here that this is my formula for decay. Right, with everything is the same amount. A is the initial amount, R is the growth rate. Remember, we write it as a decimal, not as a percent. And T is the time in years. And the only thing that changes is notice that instead of a plus here on the inside, we have a minus sign. All right, and just like in the decay or in the growth model, where this was our growth factor, this part right here, this 1 minus R, this is called the decay factor. It's like the fear factor, except it's the decay factor, or something. But anyway, that's called the decay factor. So if there's a problem that says, hey, what is the decay factor? It's just that 1 minus R, that piece inside the parentheses. All right, so let's look at an example here then, where we might use exponential decay. Here's a good one. A fully inflated child's raft or a pool is losing 6.6% of its air every day. So I don't know how they figured this out, but you're losing 6.6% of your air every day, so it's getting less and less inflated. It starts off with 4,500 cubic inches of air. All right, so that's the volume to begin with. All right, write an equation to represent the loss of air each day. So I want to write an equation that tells me after so many days how much air do I have left. Okay, so if I want to write this equation, let's write down what we know first. First of all, my initial amount, the amount that I'm starting with, is 4,500 cubic inches. So the amount that I'm starting with, A, is equal to 4,500 cubic inches. And we'll just write it as, we'll just write it as inches cubed, like that, okay? And then my rate is 6.6%, but we would never write 6.6. Remember, we want it as a decimal, and if we divided that by 100, we'd get 0.066 for R. And that's all I need. Remember, I'm going to leave Y as a variable and T as a variable right now, so that I can plug in stuff for T and figure out what Y is, my amount that I have left each day. So Y equals, then, my initial amount, which was 4,500, times 1 minus R, which was 0.066, raised to the T. And that's a fine model, but you might simplify it to be Y equals 4,500 times 1 minus 0.066. That is 0.934 raised to the T. Okay. And now that we've got a model, all right, so this means I can plug in the value for T or for Y and figure out the other one, whichever I didn't plug in. I want to estimate the amount of air left in the raft after 7 days. Well, that's just when T equals 7. Right, T is in days, and so per day, and we want 7 days. So when T equals 7, well, that's just going to be Y equals 4,500 times 0.934 raised to the T, and T we said was 7. And so if you plug this in your calculator just like that and you use parentheses in the right spot, it should spit back 2,790 about cubic inches. Okay. All right. So 2,790 cubic inches is how much will be left in the raft. So you're losing almost half of the air in just a week's time. And that's it. So the only example for exponential decay.